2.6 Nonlinear inequalities. Solve this inequality. Well, the zeros are x equals 5 and x equals 3, and we can equal those. We can include those in our solution because of the equal to in the inequality. Now let's plug these on a number line. We have 3 and we have 5, and we can include those. Now there's two ways to solve this. We can appeal to the graph of a quadratic, and we know that this quadratic opens up. So it opens up and it crosses through these two zeros. So now the function is above the x-axis in this region. In between 3 and 5, the graph is below, so the values are negative. And then over here to the right, the values are positive again. So it goes positive, negative, and then positive. And we want the negative values. So that the answer is going to be 3, 2, 5. Example 2, solve x squared minus 9x plus 10 is greater than 46. Well, we don't compare stuff to 46, we compare stuff to 0. So we have x squared minus 9x minus 36 is greater than 0. Now we can factor this into x plus 3 and x minus 12. And we have the same thing, except we can't include negative 3. We can't include that because we don't have the equal part. And we cannot include 12 either. But we have zeros now. We have negative 3 and we have 12. And again, this is a parabola that opens up. And we want the positive values. Now this parabola is above the x-axis, below, and then above. The answers are going to be negative infinity to negative 3, and then union with 12 to infinity. That's where the graph is above the x-axis and the y values will be positive. Solving a polynomial inequality using end behavior, we have example 3, and we're going to solve this cubic polynomial. Let's get everything to one side so that we're comparing to 0. We have minus 3x squared from this side. Minus 22x and then plus 24 is greater than 0. Well, we got to find some zeros. Let's try 1. 1, negative 3, negative 22, and 24. 1, 1, negative 2. We have negative 2, negative 24, negative 24, and we have a remainder of 0, so we found a 0. Now we have x minus, what do we got? A difference. I need x minus 6 and x plus 4, and that factors this quadratic here. So we have x equals 6, x equals negative 4, but we don't have equal to with this. There's no equal to. So we're actually not going to be able to use these values, but these are the zeros, so the function can change signs over the zeros. So we have negative 4, we have 1, and we have 6. Now, the ending behavior for an x to the third polynomial is, well, we're going to be up here to the right and down here to the left, because that's what x to the third looks like for ending behavior. Now, all of these zeros count once, so they'll all be cut through. So we'll cut through, cut through, cut through. And we want to know where the function is greater than 0, or in other words, above the x-axis. So the answer is negative 4 to 1, and then 6 to infinity. Example 4, solve this. Well, let's get everything to one side, and we can factor a 2x out. We have x squared minus 6x. Now, when we add this over, that'll be plus 16x, but we're taking a 2x out, so that's going to be plus 8. We have 2x, and then we have x minus 4 and x minus 2. And all this is now less than or equal to 0. So we have 0, we have 4, and we have 2. And we can include these because we have the equal to part. So let's throw these on a number line. We have 0, 2, and 4. Now this is another x to the third. So the ending behavior at the zeros looks like that. Looks like this. All of these count one time. So we have cut through, and cut through. And now we want the values that are negative. We want to know where this graph is below the x-axis. So negative infinity to 0, and we can include 0. And then 2 to 4, and we can include all those because we have the equal to part on the inequality. Polynomial inequalities with unusual solution sets. Example 5, solve this one, less than 0. Well, let's find the zeros. This doesn't factor, so we have negative 2 plus or minus square root of b squared, 4 minus 4 times 1 times 3, and that's all over 2. 2 times a. Well, that's equal to 2, negative 2, plus or minus the square root of. We have 4 minus 12, that's negative 8 over 2. So we have negative 2 plus or minus 2i square root of 2 over 2. And then finally, we can divide by 2. So we have negative 1 plus or minus I square root of 2. But the point is, the solutions are imaginary, and that means this does not cross the x-axis at all. Well, if it opens up and doesn't cross the x-axis, it has to open up above the x-axis. If it opened up and then was below the x-axis, we would have some x-intercepts. We don't have that. So when will this graph's y values be negative? No, that'll never happen. So no solution. Now, when you decide that the solutions are imaginary, another way to get no solution is just pick any x value. The easiest one would be 0. So you have 0 plus 3. Is 3 less than 0? Absolutely not. So there's no solution. Example 6. What if we had x plus 6 times x plus 6, and that's supposed to be greater than 0. So we have x plus 6 squared is greater than 0. Well, this will always be positive, greater than 0, except for one value, negative 6. So we just have to skip over negative 6 because it says don't include the zeros. So negative infinity to negative 6 to infinity. Now if it said greater than or equal to 0, that negative 6 would be okay, and the answer would be then negative infinity to infinity. Solve a rational inequality. 3x plus 4 over x plus 2 minus 3 is less than 0. We need a common denominator. So we'll multiply by x plus 2 over x plus 2. On top we have 3x plus 4 minus, we'll distribute the negative 3, minus 3x minus 6. And then we have negative 2 over x plus 2 is less than 0. So the only place we have to look is at the vertical asymptote. And at vertical asymptotes, you can have all kinds of combinations. You could have a positive and then a negative. You could have a negative and then a positive. You could have positive and a positive. You could have negative and a negative. But we need to find out what is happening on each side of this vertical asymptote right here at negative 2. Now you can never equal a vertical asymptote. We can never include it. I don't care if it says equal to here or not. The value in the denominator, what makes the denominator 0, you can never include in the answer. So let's plug in a negative 3 and maybe we plug in a 0. Now with negative 3, that makes the denominator negative. Negative over negative is a positive. When we plug 0 in, we get negative over positive, and that's going to be negative. Now we want negatives. We want less than 0, so our answer is negative 2 to infinity. Example 8, we need common denominator, but we'll minus the 1 over first. We have x plus 5 over 2x minus 6. Minus 1 is greater than or equal to 0. And now we can multiply by 2x minus 6. 2x minus 6 on top and bottom, of course. On top, we have x plus 5 minus 2x plus 6. And we end up with 11 minus x over 2x minus 6. And that has to be greater than or equal to 0. So one of the zeros is 11, and we can include that in the answer because we have this equal to part. But you can never equal a denominator. So what makes a denominator 0? Well, we add 6, divide by 2. That's going to be 3, but we can't equal that. So when we get our number line here, we have 3, and we cannot include that. And then over here at 11, absolutely we can include it. Now let's test 2. Let's test maybe 4, and we'll test 12. When we test 2, we get positive over 4 minus 6 is negative, so that's negative. When we test 4, we get positive over positive, that's positive. And then when we test 12, we get 11 minus 12 is negative. 24 minus 6 is positive, so we get a negative. And we want the positives. Our answer is 3 to 11, and we can include 11. When we have the equal, we can include the top. But we can never, like I said, include the value that makes the denominator 0, because that's a vertical asymptote. at 3. Example 9, we have, how about x equals 8 divided by 6 is 4/3. And now, because we don't have the equal to, we cannot include the zeros. And then we can never include what makes the denominator 0. So we can't include -1, we cannot include 6. But the graph can change signs across both vertical asymptotes and across zeros. So we need to include these in our analysis even though we can't actually equal these values. So we have 4/3, -1 4/3, and we have 6 over here. So how about we test -2, 0, how about 2, and test 8. So -2, here we go. That's going to be negative over a negative and a negative. That's a negative over a positive, which is negative. 0 is going to give us negative, negative, positive. Negative over a negative is positive. Plug in 2, we get positive over negative times a positive. That's going to be negative. And when we plug in 8, everybody's positive. So we got positive, and we want positives. Our answer is -1 to 4/3. Don't include either one of those. And that's union with 6 to infinity.